Okay, welcome to the class meeting 7. What is? Of EECE574. Something is very wrong with our camera. I believe somebody. Yeah, something's wrong with the connection. Yeah, it's gone, I believe. Yeah. Anyway, quiz 1 was taken last Tuesday. And that was our 7th class meeting. However, for convenience in numbering, I will number today's class meeting as number 7. Homework 6 will be posted soon and due next Tuesday. Handout for today's class meeting is updated and uploaded here. If you click this, as you see, yeah, here you have, yeah, something's very beautiful. Anyway, password is as you expect, 6. And lecture videos are available at CISL.postech YouTube channel. Unfortunately, there was no voice after 44 minutes on the last class meeting due to our technical difficulty in recording sound. And it seems today we have a camera problem. That will not affect much, I guess. Okay, anyway, so today I brought the wired microphone. So today, even though there will be no video or sometimes video, but audio will be definitely there, okay? At the last meeting, one of you asked why stationarity so important, why I ask whether some random process is stationary or not repeatedly. And I partially answered the question, and the answer is this. We observe usually a real world problem. We have a real world problem and we model some part of it as a random process. And what we are going to do as an engineer is statistical inference. So we want to do some inference. We want to guess something. We want to predict something. And the problem of a random process, as you've seen in the definition, it consists of infinitely many random variables. And also, to fully characterize it, we need, in general, enormous information. However, if we have a stationarity, then even though it's still complicated, it seems we can do something, at least in second order, for example. Many linear estimators, linear signal processes utilize what? Only up to second order properties of a random process, which means a mean function and autocorrelation or covariance function. Then if we have at least second order at least Y-sense stationarity, then what? We only have one constant, that is the mean function, and the other is a single variable function called the autocorrelation. So it seems we can do a lot then. Got it? So stationarity is important in statistical inference. Of course, some random processes, even though it is far from stationary, can also be statistically processed to do some inference. And we are going to see one of the examples. Got it? Also, not only the stationarity, but also so-called ergodicity or egodicity is very important for the statistical signal processing. And we are going to cover it after we finish this section 6.6 in the Peebles textbook. Got it? By the way, what is intelligence? Or what is the artificial intelligence or machine learning models to do? That is also statistical inference. So the basic tasks to be done will be detection or classification and estimation, which may include smoothing, predicting, filtering, and everything. So probabilistic or statistical inference is the main idea in artificial intelligence and main idea of intelligence. So when we say somebody is intelligent, what does that mean? It no longer and it never meant somebody memorizes many things. Somebody has some idea to predict what will happen or guess what was happened, something like that. Got it? And that are all inferences. Got it? Okay, overview. We are still covering chapter 9 of populist textbook. And it seems we will be covering up until the midterm. Okay. I really want to teach sequences of random variables to you. Anyway, by the way, I'm going to review strict sense stationarity because it appears in quiz problem 3 related to the Gaussian random process. So what is strict sense stationarity? And it seems that I somehow confused you because I defined it in terms of the nth order distributions. However, the key idea and the major theoretic definition of strict sense stationarity over random process is this: x of t and x of t plus, sorry, let me use negative, t minus delta have the same statistical property. For all that. That is the definition of strict sense stationarity. So let's consider this problem, this example. Suppose you have a random process very easily defined as this one. And here, data is uniform in the interval 0 to 2 pi. My question is this random process strict sense stationary? And there are two approaches. You can use this definition, or you can use the other definition by deriving every nth order probability density function. Which one is easier? In this case, it's easier to use this definition. So let's see. Let's define y as x of t minus delta, which is a cosine 2 pi f0 t minus delta plus theta, which can be also written as 2 pi f0 t plus theta minus 2 pi f0 delta. Now, what is the distribution function of this random variable? You may say that since theta is considered a scatter plot of theta, 0 to 2 pi. So if you subtract 2 pi f0 delta, it moves down, right? However, due to the modular property inside the argument of trigonometric identity, so you can add any multiple of 2 pi, right? So actually, this can be replaced by a uniform random variable on the interval 0 to 2 pi again. What does that mean? X and y have the same statistical property. You cannot distinguish whether what you are observing is x of t or y of t for every delay delta. So this random process is strict sense stationary. And actually, this argument appears in our main textbook written by Populist. So if you studied not only the Peebles textbook, but also the Populist textbook, probably you've seen this already. However, since I didn't emphasize this definition, I kind of gave different ways to prove or solve problem 3 in your quiz by assuming or by making the random process a Gaussian random process. So let's see, before we move back to the Poisson process and counting process, let's see take a look at the problem 3. That's problem in the our quiz. So this is the problem. So you have two real random variables, x and y. And x and y are IID, zero mean, and the variance is p. And we define two random variables from x and y. Here r is square root of x squared plus y squared. And theta is arctangent 2, and some of you have seen it from MATLAB programming or some other definitions. Somebody never seen, but I believe this quiz was a good chance for you to educate yourself. Anyway, this theta is the angle of the point x comma y. So let's consider two-dimensional plane. If this is x comma y, then this is r. And this angle is theta. Got it? And this theta can range from 0 to 2 pi. Be careful. The normal arctangent, sometimes depending on the definition, only periodic with period pi, right? However, arctangent 2 is not like that. Okay, it can be any number, right? Anyway, so this is the situation. And the first question was easy. You could find it very easily that r is a Rayleigh random variable and theta is uniform, and they are independent. You can directly derive the joint density, like r cosine theta, r sine theta, and r, I believe. Then you have here, they are independent Gaussians. So you have 2 pi p, I believe, e to the 2p. Here, r cosine theta squared. So you have 1 over 2 pi and r over p e to the 2p of r squared, something like this. So this part becomes the density of theta, and this part becomes the density of r, and the joint density is factored, which means that they are independent. Okay, so you can easily see and also easily find the PDF of r and theta. And then you are asked to compute the mean of r, the second moment of r, expectation of cosine theta plus any phi, cosine 2 theta plus any phi, and you have seen that these are zeros, right? And this is p. Sorry, this is p. Sorry, okay. Something like that. And in the second problem, the objective was actually the derivation of this equality. But anyway, so sketch the sample path of the random process. So you could draw any sample path, some sinusoidal function, right? And what is important is that this period is t, and which is the inverse of f0. That is the key. Other than that, the amplitude could be any number because r is a Rayleigh random variable with no bound, and this initial phase could be anything because theta ranges from 0 to 2 pi. So this is a typical a sample path of random process W. And by the way, what is the mean path? If you take the expectation, then due to the independence of R and theta, right? If you have two independent random variables, you take functions of each random variable, the result is still independent. So this R and the second factor is independent, which means that expectation of R and expectation of cosine 2 pi f0 t plus theta. And we've already seen the second factor is 0. So this is 0 for all t. So how different is this mean path from a typical sample path? It is unlikely that you observe 0 function as a sample path. However, the mean path is 0 for all t. And using the result in problem 1, derive the autocorrelation function. So you want to derive the autocorrelation function. And if I remember correctly, it's p cosine. Am I correct? Do I need over 2? Let me just think. Yeah, probably not. 2 pi f0 tau, something like that. Yeah, I'm not sure. It would be like that. So as you see from these two, W is y and stationary. You can easily justify because that is the definition. Mean constant autocorrelation function is a single variable function of time difference. Now, the subproblem E may look difficult. However, you can just expand it like this using the Euler's identity. And then you have 4 terms, where if you take 2 terms, you have x cosine 2 pi f0 t minus y sine 2 pi f0 t. And then you apply trigonometric identity like this, 2 pi f0 t, and you have arctangent 2. So what? You have r cosine 2 pi f0 t plus theta. Done. Okay. So your random process W can be written in terms of r and theta, and also in terms of x and y. Got it? As when I started this course, I told you that since I'm a communication engineer, I'm going to make this course more close to the communication theory course. So I put it there, put some problem like that, which is very closely related to the communication system. But anyway, I believe you could solve it up to now. Now, the problem 3 was a headache to you, I guess. And the first subproblem was to derive the first order PDF of W. And many of you have struggled because there are many approaches, and one approach is very easy and the other is not. So, by the way, how did you solve the first one? How? Okay. Yeah. So the idea is like this. This is complex Gaussian. And if you plot a 2-dimensional histogram, then what? It is centered at the origin. The 2D PDF is centered at the origin. It is rotation invariant. So you have some PDF with contours like that. And now, what is this one? This term just rotates this x plus jy and it doesn't affect the histogram because the histogram is already circular symmetrical with respect to origin. What does that mean? If you take the real part, then if you sample at some t0, right? And if you take the real part, then what? It is a zero mean Gaussian with variance p, right? So this is simply the PDF of W of t. Sum W is square root 2 pi p e to the W squared divided by 2p. Done. Right? Because sigma square was p, right? So this is the first order PDF. Anything wrong? I believe it's correct. And second order PDF. So we want to sample at some t1 and t2. And we want to find the joint PDF of two random variables, W of t1 and W of t2. So what can we do? And there are many ways to solve this problem. And one of the idea is like this. So W of t1 is what? Real part of x plus jy e to the j 2 pi f0 t1. And W of t2 is what? You have the same factor. And here goes the trick. Like this. Right? So you add and subtract t1. And then what? And then you have x plus jy e to the j 2 pi f0 t1 and e to the j 2 pi f0 t2 minus t1. Ready? And you focus on that one appearing here again. And what happens? This is a complex Gaussian random variable. And same random variable, you just rotate it, right? You just rotate by the angle 2 pi f0 times t2 minus t1. So if you name this one as, for example, z, then this is z e to the j something. Means real part of z plus this is real part of z, and here you have real part of z cosine 2 pi f0 t2 minus t1 minus, is it minus? Just a second. Yeah, I believe so. Imaginary part sine 2 pi f0 t2 minus t1. And you know that the real part and imaginary parts are independent and they are zero mean. So if you consider correlation of these two, the correlation coefficient is simply that one. Okay. So here, these two random variables are in general correlated with correlation coefficient, this value, I believe. Then you know from the joint PDF of a correlated Gaussian, if you just plug in the correlation coefficient and variances, you get the density. Got it? And I do not remember exactly what was that. Yeah. Anyway, the so far it's okay, but this subproblem C was a headache to you. So W of t is Gaussian or not? And your answer was what? It's Gaussian. Why? Why is Gaussian? So consider you take n points because we want to use Kolmogorov's idea to show this is Gaussian. So you take capital N samples, or let me use lowercase n because it may confuse you. So some N samples, and what happens? As you've seen, let me use capital N. Okay, sorry. The ith sample is merely what? X plus jy e to the j 2 pi f0 ti. What does that mean? You have a single complex Gaussian random variable, just rotate it, and the real part of it is taken. And what does that mean? And here we'd better remember the real part taking operation. And what is that? If you have some formula like this, real part of z, you can rewrite it like this. And what is this? This is okay. Probably I'd better teach you what is the complex Gaussian random variable later. But anyway, so let me skip the detail. The trick is that you have a single complex random variable, and just you have some scaling factor, and you take the real part of it. So it's very similar to something like this. You have a Gaussian random variable, and you have some constant vector, and you have y. In that case, is this Gaussian random vector or not? This is constant vector. This is Gaussian, real Gaussian random variable. My question is that, is this Gaussian random vector? And we've already seen by using the characteristic function, even though this is singular, this is Gaussian. We can do the same thing for the complex Gaussian. So actually we are done. Okay, anyway, this part could have been difficult, but still we could solve this one because this is strictly stationary, and you can prove or use this result and y-sense stationarity to show its strict sense stationary, or you may directly claim that since theta is uniform from 0 to 2 pi, it's strictly stationary. You could do that. Anyway, so this problem, this especially the C part, kind of forced me to teach you what is a complex Gaussian random vector and process. So I'm going to cover it. Okay, so our chapter 9 will be lengthened more. Anyway, so we've covered up to here, and here goes the preview. Unfortunately, the preview is kind of review because I've taught this part already, but the voice was removed. So I'm going to cover it again. And our video camera is still malfunctioning, but anyway. So we are going to talk about a counting process and associated discrete time random processes called arrival process and inter-arrival process. This counting process may be a discrete time process or a continuous time process. However, these two associated processes are discrete time processes, or in many cases, sequences of random variables, which means that even though it is discrete time, usually its time index starts from a finite number, usually 1, and it's a natural number. Got it? And we are going to learn a special counting process called a Poisson process. It is a continuous time Poisson counting process, and it has a very interesting property. Its inter-arrival process is so-called memory. It has the inter-arrival process consists of IID random variables, and especially an exponential random variable. So it has a memory least property. And also, this Poisson process as a continuous time random process, it has increments that are independent and stationary. So it's a Levy process. We are going to cover it. And the last question is it wise and stationary? So we can do some statistical inference easily. Unfortunately, it is not. However, due to the interesting property of this inter-arrival process, we can do many statistical inferences, assuming our counting process is Poisson. Okay, it seems we really need to report to the department. Yeah, something seriously wrong. Okay. So here goes the revised handout for the section 6.6 of the Peebles textbook. So let's consider the examples. First, you are a teller in a bank, or you are a cashier in a supermarket, and customer arrives to your queue. Got it? And you record in a continuous time axis the time instance of your customer's arrival. Okay, so for example, your bank opens at 9 a.m. and that is time 0. Of course, no customer in your queue. Then it opens and suddenly some guy comes up to your queue in 9 a.m. 2 seconds. And that time instant becomes what? The first arrival time, or the first count time. Got it? Sometimes we say arrival time or count time. Got it? And then second customer arrives, third, fourth. So given that the counting process means you construct a continuous time random process. So this is the time axis, and here you have another axis. And the value of this sample path can take only integers, especially in this case, a natural number and 0. From 9 a.m. to 9 a.m. 2 seconds, the value is 0. And at time 9 a.m. 2 seconds, it jumps to 1 because you have one customer, right? And the problem is that a problem in the defining a continuous time sample path is that how do we put our equality? So our convention is that it's exactly at time 9 a.m. 2 seconds, we define the sample path jumps to 1. And it becomes 1 for a while until the second customer arrives, which means that this function is piecewise constant and right continuous. Right continuous means that if you move from the right side of T1 and converges to T1, the value of the sample path is the same as the sample path at time T1. Got it? So it's a right continuous piecewise constant function. Here goes another example. The occurrence of lightning strike within some prescribed area. So our post-tech campus, from now on, we count the number of lightning strikes. And in the daytime, it will be 0, especially in summer. We will have a lot of lightning strikes because we are all sinned. And failure of some components like that camera today, right? In our LG research building. And now you can build a counting process, or you can draw a graph that is a function of time, and the value means the number of failed component or number of lightning strike, number of customers, right? And of course, these functions have some uncertainty, and we may want to model that function with uncertainty statistically. Now we have a concept of random process to use, right? So now we have a random process, and we have a so-called counting process. By the way, I'm going to talk about another counting process. So consider this one. You have some, let me see, is it X, Y? Let me define a random variable y sub n for n integer. And what we do is that y sub n is a Bernoulli 1p. What does that mean? And also it's IID, independent and identically distributed. What does that mean? At every time index n, we toss a coin with some bias, that is p, and this yn can be 0 or 1, right? Now, we define a sum process. And sum process is very simple. Given a discrete time process, you do something like this. Got it? And in many cases, we define 0, 4, and 0. Now, what happens? Let's consider a sample path of this S sub n. This is n. At 0, it's 0 because we defined it like that. And at time 1, what can happen? If y sub 1 is 0, then it's still 0, right? If y sub n is 1, it jumps to 1. And if y sub 1 is 1 and y sub 2 is 1, what happens? It jumps to 2, or something like that. Okay. This is what? This is a discrete time counting process. So here, it seems that every counting process is a continuous random process, but it is not. That's what I want to say. Got it? A counting process could be a discrete time process. So be careful. But in any case, we have a counting process and associated what? Arrival process or an interarrival process. So let's see the figure in the next page. Just to focus on the right half plane, okay? Because I haven't yet extended it to the t negative. So here, at time t equals s sub 1, first customer or lightning strike occurred. So it jumps to 1. And at time S2, the second customer arrives, so it jumps to 2, something like that. Got it? So usually, this convention means that at some time t equals s sub I, right? The value is this one, not that one. Got it? So it's right continuous piecewise constant function. And this is a sample path of the counting process, but we may just not consider this one by just focusing on that one. So the difference is that we only have a single time axis, and we put what, or we mark points of customer's arrival. So here is the first point, second point, third point, fourth, fifth. So you have only points scattered on the time axis. So sometimes this is called a point process. By the way, since our points are scattered in a one-dimensional line, this is definitely one-dimensional, or simply just a point process. By the way, you can scatter points on a two-dimensional plane. And of course, there are 2D Poisson point process. Here, we only learn, for example, only learn 1D Poisson point process or Poisson process. Anyway, and by the way, we can draw one more line, or we may define something like this. Let's define this interval, the length of this interval as x1, and this interval as x2, this interval as x3, this interval as x4, which means that x of n equals s of n minus s of n minus 1 for n greater than or equal to 2, right? And for n equals 1, we define it as 1. Got it? And what does that mean? From time 0, the first or the new customer arrives after x1 seconds. And then from that time instant, another new customer arrives in x2 seconds. So this is arrival and arrival. And this interval is inter-arrival time, right? So xn is called inter-arrival process. So these two figures shows that you have here a counting process. And here you have an arrival process. And here you have an inter-arrival process. By the way, we can construct a counting process from an inter-arrival process. For example, you have an inter-arrival process X. Then what is S? Simply sigma xi from I equals 1 to n. Then we can construct n of t by using I equals 1 to infinity u of t minus si. So here u of t is a right continuous unit step function. Got it? So it's 0 up until the argument becomes 0, and it jumps to 1 when the argument becomes 1. So this is the construction of the counting process from the inter-arrival process. By the way, as I told you, since this is called, or mostly called, counting process, this arrival process is called count time process, and this inter-arrival process is also called inter-count time process sometimes. Got it? And this is also called point process. So there are many names indicating the same thing. Got it? So we covered 2 pages. And here, you have to be careful. Whenever I talk about an interval, usually I will exclude the left-hand point, and include the right-hand point. Let me see, something's not correct. Interval in, yeah, sorry. And this convention will be continued. And now let's consider extending our counting process to the negative time interval. So as you see here, our usual convention is that our time origin, t equals 0, is chosen such that no arrival occurs. Okay, that is the convention. Now, for example, you just have chosen your noon or 12 p.m. of today, and fortunately there will be no, in 15 minutes there is no lightning strike, and then you have marked the time instance of the next lightning this way. And then what was the time instance of previous lightning strike? For example, here. Now our question is that, are we going to mark this as s of -1 or s of 0? And our convention of excluding left-hand point and including right-hand point dictates us to mark this as s of 0, so that we have all arrival times or counted times at which really arrival happened. Got it? So this could be looking strange, but as you see here, if we define a counting process at time 0 as 0, and for the positive we've defined like that, then this is the correct way. So if t0 is negative, and then n, that is the count random variable, or that is count at t0, is some negative m, where m is a non-negative number, which means that it could be 0, -1, -2, Got it? And here m means, the negative m means you have negative m, which is m is non-negative. Just a second, m is non-negative. Yeah, m is non-negative, and you have m arrivals during this period t0 to 0. So you have t0 to 0. Got it? And let's go back to this figure and see. At time instant here, which is not a negative value, right? What must be the n of this t? And we see from here to 0, we have single arrival. So we take the negative of it, that is -1. Got it? So in that way, we can extend the notion of counting process to include the negative time axis. However, usually when we talk about an arrival process and an inter-arrival process, we usually restrict our attention to the positive and non-negative time axis. Another one is that you may say, wait a minute, it seems it's possible to have 2 or 3, more than 1 arrivals at the same time, and which is the case in many real-world situations. So given counting processes, there are 2 classes of counting processes. One that does not allow simultaneous arrival. Second, simultaneous arrivals are allowed. As I told you, in many applications, real-world applications, simultaneous arrivals happen. However, in our Poisson random process, as we will see, the probability is 0. So there is a class of counting random processes that does not allow simultaneous, or that does not consider simultaneous arriving. In that case, we can have a better formulas. That's what you need to remember. Anyway, in any case, whether it is a discrete time or a continuous time, a counting process has this property. It's integer valued for all t, and it's non-decreasing because we only count up. Got it? If no arrival, no simultaneous arrival happens, then every sample path increases by 1 if it increases. Now we formally define an arrival process or a point process or a count time process S sub n. And as you see, if no simultaneous arrival, then S1 is positive and S2 is greater than S1 because no simultaneous arriving. Got it? And in this case, probability of S sub I less than S sub I plus 1 is 1. And here goes some at first glance, confusing results. N, and this is time index, S sub n equals n. What does that mean? And whenever you see this type of equation or equality, go back to this figure. Now this is n of S1. What does that mean? The first customer arrived and we defined the value as what? 1. N of S4 must be 4, right? N of S5 must be 5. N of S0 must be 0. N of S negative 1 must be negative 1 because it's right continuous. So this strange looking equality is correct. Got it? Let me test the camera again. Oh, it does not work at all. Okay, it's gone, I believe. Yeah. Which one? Okay, something's seriously wrong. Yeah. Anyway. Okay. If t is in this interval, it's greater than equal to S sub n, and less than, strictly less than S sub n plus 1, then its value must be n, right? Is it correct? Also, again, recall that figure and focus on, for example, S1 and S2. What is the value? 1, right? Now, this looks strange, but you may do something like this. As some t0, you arbitrarily, for example, select t0 from the non-negative axis, and you consider what is the neighboring points, and also what is the relation between your count variable number. So suppose you have chosen this as t0. Then here is 3, right? And your t0 is greater than S3 and less than S4. And our question would be, what can we do with the equalities? Something like that, right? So we move this one to T S3, and what happens? We may have equality here, right? And let's see, am I correct? I hope so. Yeah, got it? And we can't have equality here, something like that. By the way, I've just shown you from the counting process, from the arrival process, we can construct a counting process. Got it? And also here, two events, Sn less than or equal to some T0 and n of T0 greater than or equal to n are the same events. So as I told you, given a single real world situation, you can view it by using it a counting process or an arrival process or an inter-arrival process. So what does this mean, by the way? At some T0, your value is greater than or equal to n. What does that mean? How many arrivals have happened? At least n arrivals. What does that mean? At T0, Sn must be less than or equal to T0. Got it? So in this way, by going back to this figure again and again and again, you can easily understand the equivalence of two events. And now, since these two events are the same events, the complement events are the same. So you complement this one, which means that S of n is greater than T0. You complement this event. N of T0 is less than n. They are also identical events. By the way, in manipulating, especially Poisson process or related counting processes, these kind of tricks are very, very useful. So you are asked to compute some probability of event. It seems very complicated. You convert that event to an equivalent event, or you convert that event to what? Complementary event, and take the probability and you subtract it from 1, then you get the desired probability. Got it? Now, we formally define inter-arrival process from an arrival process like this. As I told you, x1 is defined as S1, which means that we consider only a counting process that is defined on a non-negative interval. And we have that for n greater than or equal to 2. If no simultaneous arrivals, then inter-arrival process is a sequence of positive random variables with probability 1. And the arrival process is simply the summation up to n, as we've seen in the deterministic series and sequences relation, right? As we've learned in high school math. Given a sequence, we can define a series. Given a series, we can derive a sequence, right? By the way, if an inter-arrival process Xn has IID random variables, then it is called the renewal process. Or sometimes the counting process, associated counting process is called the renewal process. Because we are looking at the same thing and interpreting it differently using in terms of counting process and arrival process and inter-arrival process. In many cases, they just say the counting process is a renewal process, even though strictly speaking, renewal or not is defined given an inter-arrival process. Anyway, now here goes also a very important definition related to a counting process. So far, given a phenomenon, we view it as a counting process, arrival process, and inter-arrival process. Now let's focus on this counting process. So given a counting process, we define so-called increment during an interval. Here again, interval has what? Left hand excluded and right hand included. This is our convention, used again and again when we deal with a counting process. So given a sample path, something like that, we select 2 time instants. Let's say, okay, this is T1 and that is T2. And my question is, what is the increment on this interval? T1 to T2. What is the increment? Increment is what? N of T2 minus N of T1, which is what? Number of arrivals within this interval. Got it? That is increment. So what is that? 1, 2. Got it? So in this case, this is 2. Now, given fixed T1 and T2, what is this one? It's a subtraction of random variable from a random variable. So it's a random variable. So an increment or the increment given an interval, right, is a random variable. So given a counting process, how many increments can you define? In this case, uncountably infinite, because it's a continuous time process. Given a discrete time counting process, you may define countably infinite increments. With infinite increments, we rarely can say something useful. So here goes the non-overlapping intervals. So consider you have T1 and T2 and T3 and T4. And we visualize, and here goes the interval. And for example, something like that. And these 2 intervals in this example have no intersection. If these 2 intervals, semi-open intervals, have no intersection, which means that intersection is empty set, then we have what? Non-overlapping intervals. Got it? What if we have 3 points and consider 2 intervals like this? Are they non-overlapping? We share these 2 points, but here it is included and here it is not included. So still we have non-overlapping intervals given 3 points, right? So we are happy here. Got it? But what happens given that we have T1, T3, and T2, T3? So the first interval is from here to that points, and second interval is from here to that. They are not non-overlapping. They are overlapping. Got it? So now you have a clear idea of what is an overlapping interval in the time axis or not when you talk about increment. Because given an interval, we define an increment. So here, given this interval, we have an increment. What does that mean? During this interval, how many new arrivals? How many arrivals? During this interval, how many arrivals? So we have associated increment here and associated increment here. And in some counting processes, here goes a very interesting property. If the intervals are non-overlapping, if the intervals are non-overlapping, the increments are independent, sometimes. And this class of random process, this class of counting processes are very, very interesting. So we define and give a name. And another one, So here is the set of all counting processes. So here is the set of counting processes that has independent increment property. Okay, so every pair of non-overlapping intervals, or given any finite number of non-overlapping intervals, given each interval you have random variable, right? And these random variables are independent. Here goes such random processes. And second one is that this is also interesting. So given a single interval, left excluded, right included, you have an increment, a random variable. And interestingly, the probability distribution of that random variable is parameterized only by T2 minus T1, the length of the interval. Then we say the counting process has stationary increment property. So here goes another set, stationary increment property. So we have a counting process and defined two subsets. One, having independent increments. Second, having stationary increments. Got it? And then what do we want to do for the intersection of that? We want to give a name, and this is Levy processes. So this intersection of independent and stationary increment, they are Levy processes. Be careful. Here, I started from counting process, but some of you have already observed that this is not needed. Given any random process, you can define that. Increment may be a negative number, no problem. So actually, I have to delete this counting. So given all random processes, there is a very small subset has independent increment property. Very small set, stationary increment property. And then we have smaller set, Levy process. And of course, we may have something like this, counting process. Got it? So counting process may be a Levy process. Counting process may have stationary increment property. Counting process may have independent increment property. And here goes some examples. Let's go back to our sum process of the Bernoulli process. So binomial 1p, that is yn, and we have, so we can define actually xn, right? Because before we call it y, but it is what? It is inter-arrival time, or I'd better not say, okay, let me use it that way. Yn, okay, and Sn is y1, y2, yn. So up to time index n, how many ones, right? So how many customers? Now, from this one, we can define, by the way, is it a counting process? Yeah, I believe this is counting process. So let me define differently. Yeah. I'd better say this. Yeah. So let me correct the example, because it's confusing if I define that way. Yeah, here. it's a sum, but it's not the arrival process. So n sub n. Got it? Yeah, this is better. So this counting process, discrete time counting process, here goes my question. Does it have independent increment property? So given a non-overlapping interval in discrete time axis, the increment is independent? Yes, because we assumed yi's are IID. So given a discrete time interval and non-overlapping interval, how many ones they are independent? So this sum process of a Bernoulli process, it satisfies or has the independent increment property. Now, second, does it have stationary increment property? Of course, right? Because if we increase the length of interval, what is the distribution of the increment? Bernoulli n comma p. And n is the only parameter. So it satisfies stationary increment property. So actually, this counting process is what? Is a Levy process. Got it? And we are going to see, actually, we are going to just, given the fact that the Poisson process is a continuous time counting process and also a Levy process. By the way, here we've seen in the first example, a counting process, a discrete time counting process, that is a Levy process, right? In the second, we've seen a continuous time Poisson counting process, that is Levy process. So sometimes, and I also was very confused when I was a student, that it seems that every Levy process counting process, but actually it is not. We are going to see the Brownian motion or Wiener process in chapter 10. And that is not a counting process, but that is a Levy process, having independent and stationary increment. So be careful with the definitions. And here goes the Poisson process. We have 3 minutes left. There are many ways to define a Poisson process because given a single real-world situation, we may model it using counting process. We may model it using point process. We may model it interarrival process. So some definition starts from interarrival process. For example, saying this. Here is an interarrival process. So each random variable x is an IID exponential random variable with parameter lambda t actually. It's lambda actually. And then they say that associated counting process is called the Poisson process. Done. So in that case, what? Just describing or just fully characterizing the interarrival process, the continuous time counting process is defined, fully characterized. And that is one way. And we know that a Poisson process has IID interarrival random variables that is distributed exponentially.
It is time to wrap up. It is time to wrap up.
Sometimes we may define a Poisson process by viewing it as a counting process. In terms of what then? Of course, we may resort to the Kolmogorov extension theorem, which means that we may define the first order, second order, third order, any nth order probability mass function of that counting process. However, in many textbooks, especially our Peebles book and other undergraduate books, define the counting process, the Poisson processes counting process by using the increment. So it's like, okay, the Poisson process has independent stationary increment. And that property is like that. Okay, it seems time's up. I have to continue next week. Okay, that's all for the day.